Waalaikumsalam, Azri, apa khabar? Assalamualaikum, apa khabar semua? Can you hear me? Sihat. So how's your raya? Semua dah balik ke kampung kan? Anyone else still in USM? Semua dah balik Okay, let me approve some of your friends. Alright guys, can you see the slides? Okay, that's good. Alright, so today we're gonna look into MOSFET. So last time before your break we have we have covered solar cells, and we're gonna look into MOSFET this week, and some of the other materials for devices have been partially covered when we did our presentation one. So I'm not going to cover every single device in this course, but instead you can always refer to the Padlet where your friend have shared their presentations. Okay, so I'm just going to cover solar cells and MOSFET, and the rest are practically for transistors, for example. It's still FET based like JFET and some other FETs. Okay, so the basics are similar except they are operating slightly differently, and we are looking into different output characteristics and equations and other stuff. Okay, so let's move into MOSFET now. So before we move on, let's recap a few things on what we've learned in solar cells. You should be able to answer these questions, so related to solar cells, which are the G's of the topic. Okay, so firstly, you should be able to draw a schematic diagram of a solar cell. Can you still recall the schematic? How does it look like? What should we have in a solar cell? The basics. What are the basic structures of solar cell? What should we have? Come on, let's recall a little bit before we move on. What is in a solar cell? Apa yang paling basic yang kita dah belajar sebelum ni? Yup, P-type, P-N type, silicon, PN junction, yes. Basic is the substrate, silicon. If you're working on silicon, then PN junction. Then what else you should have to be able to make the solar cell functional? So can you live with PN junction alone? ARC, good. ARC, anti-reflective coating. All right, what else? So you should have PN junction, ARC. Lagi apa lagi? Yang paling basic for all types of solar cells. What else? So once you have your junction, so once you have your carrier separation, then what else? What's next? What's next for the carriers? Where are they going? Where do you get the carriers out? On both sides? Yeah, you should have metal contacts on both sides. A set of contacts on P side and another set of contacts on N side. And these contacts, as I taught you last time, it doesn't have to be metal. It doesn't have to be metal. It may also be transparent contacts like RTO and some other transparent conductive oxides. Okay, so the basic is a PN junction, ARC, metal contacts, and that's it. The moment you have all this, you already have a basic solar cell structure. So whether it's yielding a low efficiency or high efficiency is completely another thing, because you then have to look into the losses and what else need to be improved to be able to produce high conversion efficiency solar cell, right? So what is done? So let's go to the second question. Describe operation of a solar cell. What should happen in a solar cell before you get current voltage curve out? Apa yang perlu jadi dalam solar cell? What's the very first thing? Light absorption. Yes, light absorption. Right? Can all spectrum of the light be absorbed? For example, if you use cadmium telluride or silicon, right? No. Okay, why no, Faika? Why you can't absorb the whole spectrum of the sunlight? Yes, exactly. EPH must be larger than or equal to EG. So that means if you are using silicon as your absorber materials, we say absorber materials, which means the main semiconductor used for solar cell. So if you're talking about silicon, then the band gap is 1.1. So that means the photon energies have to be equal to 1.1 or larger than 1.1. Then only the valence electron can be knocked out and ready for conduction. Okay, so therefore you can't harvest the whole spectrum just by using a single material, but instead if you go for double stack like tandem cell with two solar cells in one, that means you're going to have a top cell on a bottom cell, or you have triple junction, 3 junctions or more, 4, 5, 6, then you're going to be able to harvest a wider spectrum of the incident light. However, it comes at extra cost, because the moment you add on new materials, new junction on top of the bottom junction, then the cost is going to add up accordingly. So light absorption is the first one. Then what else? First is light absorption. Then the moment the light is absorbed, so what's next? Right, generation of electron hole pairs. So now we generate electron hole pairs throughout the volume, but we know that the generation rate of a solar cell follows an exponential decay pattern, like we've discussed last time. Gx on the y-axis versus distance into the cell on the x-axis. It's going to go with exponential decay profile as the light goes into the material. Okay, generation. So then we have free electron hole pairs. Then what's next? Setelah kita generate, apa jadi ke electron hole pairs? So they are now broken, they are now free. So we want to separate them, right? We want to separate them. So yes, carrier separation. How do you do the separation? How do you separate electron into one way and holes into one way? Who does the job? Which part of the solar cell does the job? Which part? How do you push one carrier to one side and then another one to the other side? This is done by your PN junction, right? So remember, the moment you have your PN junction, your P side will extract holes and your N side will extract electrons. So the moment you have electron hole pairs, they are free, wandering in the silicon, for example, silicon solar cell. So holes are going to be extracted into P side, electrons are going to be extracted into N side. Therefore, they are now separated, okay? And lastly, they are extracted through metal contacts on the P side and on the N side. Then you have your IV curve. So the third question, why performance of a solar cell depends on EG of the semiconductor material making up the cells. This is exactly what we've discussed just now because of the light absorption, right? So EPH and EG dependencies. How do we calculate conversion efficiency of a solar cell? Can you still recall the equation? How do we calculate the conversion efficiency of a solar cell? So eta is the conversion efficiency. Wait, why is it still black? What is it equal to? JSC times VOC times field factor over P in. So the whole thing up here is actually P out, right? The whole thing up here is P out. So it's actually P out over P in, and P out is equal to JSC times VOC times field factor over P in, and P in, if you do the measurement under standard test condition, or we call it STC, so then this STC has to be at 1000 watt per meter square, 25 degrees Celsius, and using solar spectrum of AM 1.5, MS 1.5, right, to be able to be called standard test condition. If you don't operate under STC, then it's not under STC. It's not under standard test condition. So that will make if you have a record cell, for example, if you have just produced a world record cell for certain material or certain junction, then you cannot declare as a new world record because it's not measured under standard test condition. So therefore, your new world record cell will not be able to go into the NREL PV efficiency map that I've shown you last time. Okay. Right. 1, 2, 3, 4 done. Let's go to the number 5. How do we increase carrier collection probability in solar cell? So how do you increase this? Collection probability is called it's also called QE, quantum efficiency. So how do you increase QE or collection probability? Any ideas? How do you increase? It could be so many approaches to increase the quantum efficiency. Anyone? Collection probability. What is collection probability? What do you understand by collection probability? Pyramids. Yeah, pyramid is to improve the light absorption. Pyramid is acting more optically in order to absorb more light, reduce reflection. But when we talk about passivation, because when we passivate the surface then you will reduce your surface recombination velocity on both surfaces, and in fact you can also passivate the bark, and it's called bark passivation, and this will help improve a quantum efficiency in the solar cell or collection probability in the solar cell. There are many more ways um, you can help by reducing doping level, but at the expense of series resistance in the solar cell, and there are many more ways, right? So down with solar cell, let's move on to the next one. So today we're going to look at MOSFET, and the essence of this topic, I'm going to look into MOSFET and CMOS. MOSFET is the basic building block in a CMOS. Okay. Yeah, some of you have done your presentation on MOSFET, and they are all good presentations. So I want you to go back later on and try to understand the operation of MOSFET from your friend's presentation. I'm not going to go through in details here. I'm just going to go briefly on the solar MOSFET operation, and then I'm going to jump into CMOS for further details. Right. CMOS. What is CMOS? CMOS is actually a metal oxide. If you look at this, metal oxide semiconductor field effect transistor. So it's a form of field effect transistor. Metal oxide semiconductor field effect transistor. Right? So why is it called MOSFET? So let's have a look at the basic structure of a MOSFET. So in a MOSFET, we have, well, when you talk about transistor as a basic building block in this whole thing, so transistor is a three-terminal device. Transistor is a three-terminal device in comparison to a diode that we've learned last time, where diode is only a two-terminal device, PN junction or NP junction, right? But when you talk about a transistor, it's a three-terminal device. That means it's either PNP or NPN. So you're going to have three terminals in order to operate as a transistor. So what is the role of transistor? What is the transistor doing? From presentation 1, what can a transistor do? Siapa yang buat presentation MOSFET? Please help here. What is a transistor? What is transistor's role? Farah buat transistor kan? MOSFET. What is it doing? Transistor. Yeah, Jasmine. Switch and amplify. Good. Yes. Transistor does switching and amplifying job. So it's a switch and it's also an amplifier. So ingat dua ni ya. It does switching and it does amplification. So that's the job of a transistor. Okay. So in MOSFET, we have three terminals. So we have gate here. We have gate in the middle. There. That's gate. And we have source and we have drain. Right? So when you talk about MOSFET, metal oxide semiconductor field effect transistor, so where do you find all this? Metal is usually the gate. Metal is usually the gate. But metal gate has been used last time, but in recent years, manufacturers are using polysilicon gate. So that means it's based on silicon gate. Even though it's still called MOSFET, tapi dia pakai gate ni as polysilicon material instead of metal. Last time it was aluminium, now it's polysilicon. So we're going to learn about polysilicon a little bit more in fabrication process next semester. So metal oxide semiconductor field effect transistor. So the gate is the metal or polysilicon. Right, oxide is the oxide under the gate. So this is oxide. The black region here is oxide, a thin layer of oxide, usually silicon dioxide, SiO2. So semiconductor, metal oxide semiconductor. So this is your semiconductor. So it can be p-type, it can be n-type, silicon, right? So field effect transistor. Why is it called field effect? Kenapa kita panggil dia field effect transistor? So for those who do FET, for your presentation one, Jasmine what FET kan? Jasmine, you did JFET, right? Was it BJT or JFET? JFET? BJT, okay? So why is it called FET? What is FET doing? Bukan FET bukan FET gemuk FET, field effect transistor. Kenapa kita panggil dia field effect transistor? Kenapa? Anyone? Any ideas? Why is it called field effect transistor? Field effect. Key is field effect. Because we use field, electric field, in order to modulate the channel. We use electric field in order to control the channel. Modulate itu maksudnya control lah. Control the channel conductivity, the channel presence. Either you want to have the channel or you want to reduce the channel thickness and so on and so forth. So in this case, we're going to look into operation later on, but we can apply gate voltage VG, positive or negative, in order to modulate the channel down here. We're going to see channel down here. Okay, so that's the basic. So that's why we call it field effect transistor. So it's a transistor which operates based on field effect. So that means you need to apply a gate voltage, either it's positive or negative, in order to modulate the channel itself, and the channel conductivity and the current flow and so on and so forth, in order to make the transistor operates as desired. Okay, so that's why we call it metal oxide semiconductor field effect transistor. So you can actually understand the structure by looking at its name, right? If you look at MOSFET, then try to explain to yourself why is it called MOSFET, and these are the things, right? So let's look at the introduction of MOSFET. So this is the very same thing that you saw on the previous page. So the gate is on the top here. So this is the gate. So it's either metal or polysilicon. The previous structure used metal, but the current structures use polysilicon in the fabrication now. Right. Source and drain. Source and drain are typically doped silicon. So that means you need to dope your silicon. If you're talking about if your substrate is p-type, for example, then your source and drain are typically n-type. So in this case it's called NMOS, because the channel under the gate oxide here will be made of n-type channel. So that's why we call it NMOS. So either we call it P or N. So it depends on the polarity of the channel. It's not the polarity of the substrate. So in this case, if your source and drain are n-type, so your channel will be n-type. So it's gonna be called NMOS instead of PMOS. So if you talk about PMOS, so that means your substrate has to be n-type, and your source drain has to be p-type. So therefore your channel will be p-type, and it's called PMOS. Okay, so that's the basic structure. So we have two classes of MOSFET. You can look into the operations in the presentation one by your friends. So we have enhancement mode and we have depletion mode. So enhancement mode is a normally off transistor. So that means if you don't apply any gate voltage to the transistor, it will be off by default. So to be able to turn the transistor on, you need to apply a VG or gate voltage on top of the gate in order to create a channel under the oxide. Okay, create channel under the oxide. So gate oxide, and then channel. So on the other hand, if you talk about depletion mode, it's a normally on transistor. So that means if you don't do anything, if you don't apply any voltage on the gate, it will be on in the default condition. But in order for you to turn it off, you need to apply a gate voltage on the gate, right? So it's normally on. Kenapa dia normally on and off ni, we'll see later on. So each can be used as N channel or P channel for operation. So you will have N channel enhancement mode, you will have N channel depletion mode, you will also have P channel enhancement mode, you will also have P channel depletion mode. So we're going to have all 4 modes all together, right? Right, you can see the summary here. 4 modes of operation. So on the left hand side, so the top one is N channel enhancement mode. On the bottom left is N channel depletion mode. So on the right hand side, hold on, let me improve. Right, on the right hand side, it's P channel enhancement mode, and on the bottom right is P channel depletion mode. Okay, apa maksudnya? How do you tell whether it's N type, NMOS or PMOS, or N channel? So if it's called NMOS, then it's N channel. It can be depletion or enhancement. So if you see P channel, then it's a PMOS. Okay, so how do you know whether it's P or N? Kalau tengok symbol ni, you can see from here, transistor with symbol on the right, N channel ni dia punya arrow coming in, and the P channel the arrow going out, right? So that's how do you differentiate between N or P. So N coming in, P going out, right, for MOSFET. So how do we distinguish between enhancement mode and depletion mode? Mana siapa yang buat presentation MOSFET? How do you distinguish enhancement mode or depletion mode? How do you spot? So let's see the difference between N channel depletion. Kita tengok yang kat bawah ni. Now let's see down here. So what's the difference? So they are both depletion. Okay, sorry. Let's look at this. Let's look at this group. Apa beza antara channel N channel enhancement and N channel depletion? What difference do you notice in the schematics? Anyone? Yeah, line between D and S, line between drain and source. Okay, if you look into enhancement mode ke atas, so there's the channel here, yang gelap ni, yang grey ni, is actually induced. Channel here between source and drain is called channel. This is induced, so that means you need to apply a gate voltage to be able to get a channel. So maknanya channel tu dia tak ada lagi. You need to apply VG, then only you will have a channel. So on the other hand, if you look into the depletion mode N channel, bawah ni, line ni memang dah ada. So that means the channel is already there, even though you don't do anything. So it doesn't have to be induced, but it's there already. Why is it there already? How come it's there already? Farah, do you have any idea? Kenapa dia dah ada kat situ? Kenapa dia tak induce? Oh, anyone else who did MOSFET? Saya dah lupa nama. Anyone would like to help? No, we're only on page 7 now. Kenapa channel tu dah ada kat situ? Kenapa kita tak perlu induce? What did you do to be able to have the channel there already? Anyone? Any ideas? Tak ada idea? Yes, exactly. Dope. Good. Dope. So that means when you do your fabrication of MOSFET, you have to dope the layer already. Maksudnya dekat gate oxide, you ada gate dekat atas kan, gate. Then bawah dia ada oxide. Dan bawah dia ada ruang untuk you create channel between source and drain. So if you don't dope, it's gonna be enhancement mode. Maksudnya you tak dope, then you want to induce channel formation, then it's going to be enhancement mode. Tapi kalau you dah dope siap-siap, maknanya you buat channel ni waktu fabrication lah. You did this while fabricating the MOSFET. You dope already the channel. So maksudnya laluan tu memang dah ada waktu dalam proses. Tapi on the other hand, for enhancement, channel tu tak ada waktu fabrication. You have to induce. You have to create. You have to complete the transistor fabrication. Then you have to apply VG. Then the channel will be created. So that's the difference between enhancement and depletion. So if you look into enhancement here, since you don't have doping of the channel beforehand during the fabrication, you need to induce formation of the channel. Therefore, it's a normally off transistor. You need to apply VG to be able to turn on the transistor. On the other hand, for the depletion mode, since you dope already the channel during the fabrication process, it's a normally on already. So it's not normally off, it's normally on already because the channel is already there by default. You don't have to do anything to be able to operate the transistor. On the other hand, you need to apply the VG on the depletion mode in order to turn off the transistor. Okay, so faham? Is it clear? Enhancement and depletion, P channel, N channel tu sama je. It's just the opposite of each other. Kalau it's a NMOS, then the channel is going to be N type. If it's a PMOS, then the channel is going to be P type. NMOS is equal to N channel, PMOS is equal to P channel. So it's defined by the channel, not the substrate, right? Done. So this is the operation of the channel. How do you actually induce the channel? So to be able to, so this is actually N channel enhancement mode. Kalau you tengok kat sini dia punya gambar ni is actually just a portion of the circuit dekat previous page, just the portion. So maknanya you cut straight through the device and you see, you tak nampak lah kiri kanan ni, tak nampak lah. Actually the whole thing is like this, tapi just cut nak tunjuk the cross section of the device while in operation. So you have your gate up here, so it's actually the gate. So here is oxide under the gate, so it's also called gate oxide. Kalau dalam fab, Silterra ke Infineon, we normally call it gate ox. So it's a abbreviated version of gate oxide. So it's a gate ox process. And then the blue part here is actually the channel. The channel. So down here is depletion region created with the channel. So maksudnya sebelum kita dah belajar, kalau kita induce electric field and so on, you're going to create depletion region. So this one comes in during the channel creation process, right? So then you're going to have your substrate down here. Substrate is P-type. So that means your channel is N-type. So your substrate is P-type. So it's an N-channel enhancement mode, or it's called NMOS. Okay. So macam mana kita create channel? How do you create a channel? So how do you create a channel? So right, mula-mula tak ada channel. So let's talk about N-type enhancement mode, N-channel enhancement mode ataupun NMOS enhancement. So bila you apply VG, bila you apply positive VG, so it has to be a positive VG. So what you will do is that saat saya buka agak sila senang sikit. Tak apalah, okay. Tengok sini. So you apply a positive VG. So what will a positive VG do is that it will you ada silicon kat sini kan. This whole thing is your silicon. So it's actually silicon here. The whole thing is silicon. Silicon is P-type, and you have source on one hand on the left hand side and drain on the other hand on the right hand side. So bila you apply positive VG, what it will do is that it will repel holes. Sebab P-type the majority carrier dia hole kan. So for your information, MOSFET ni is a majority carrier device. So it's a majority carrier device. So bila you apply positive VG, you will repel holes, which are the majority carriers in P-type semiconductor. So bila you repel hole, it will be repelled away from the surface. So that means it's gonna go away from under the oxide on the surface, and then at the same time you will attract electrons. You will attract electrons which are also minority carriers in the p-type semiconductor. If you still can recall, NP is equal to Ni squared, masih ingat ke? Law of mass action. So if you have a p-type semiconductor, so that doesn't mean you don't have electrons at all. You still have the minority carriers. It's given by, if you want to know your minority carrier electron in p-type semiconductor, then it's going to be equal to Ni squared over p. So if you're talking about p-type 1016, so minority carriers will be equal to 10 to the minus 4, 10 to the 4. So maksudnya you masih ada elektron lah dalam tu kan. So bukan tak ada electron. So these electrons are going to be attracted to the surface by the positive Vg. So you're going to be end up with accumulation of electrons under the surface. So let me share with you. Okay, can you see the whiteboard? Please confirm. Okay, good. So what we have is actually here. Kita tengok proses nak switch on. Nanti the rest you can go through yourself. So this is your p-type silicon. So when I say it's p-type silicon, so is this an NMOS or PMOS? NMOS ke PMOS? The substrate is p-type, therefore NMOS ke PMOS? Remember the name is given by the channel, right? NMOS, yes, it's an NMOS. So you have your gate there, and then you have, this is the oxide. A very thin layer of oxide is typically below 10 nanometer. Okay, 10 nanometer thickness. So you have your source on the left and drain on the right. And this one is p-type silicon. So what happens if you apply a positive Vg? Is a positive Vg, sorry. So okay, so it's a positive Vg. So what it will do is that it will repel holes. Hole ada kat sini, hole. It will repel holes away from the surface. If you put it positive, hole is positive, so the positive charges are going to be repelled away from the surface. At the same time, you will attract negative charges, negative carriers to the surface. So you will end up, if Vg is high enough, you will end up with an inversion layer. So it's called an inversion layer. This inversion layer is also called a channel. So the operation is sama untuk all type of transistor. Kalau you letak positive or negative, then you will attract and repel accordingly, right? The charges. So in this case, for NMOS, so this one is called NMOS because the channel is N-type and enhancement mode. So you will end up with inversion layer. Apa maksud inversion layer? Maksudnya original charge accumulated in this region near the surface is an opposite charge of what is the original charge. So originally you have p-type, the whole thing. P-type, the whole thing is actually p-type. So the whole thing is actually majority carriers holes. Tapi bila you apply Vg, you akan invert the carriers on the surface. So that's called inversion layer. You flip the carrier from the positive charges to negative charges. So you therefore creating a channel. So you create N channel. So the moment you have this N channel, the current can flow. The current can flow from drain to source. Nanti saya akan bagi satu YouTube file on the animation of the MOSFET operation, right? So electrons akan flow from source to drain. Electron, source to drain. Current, which is also called IDS, I drain source. flowing from drain to source, right? So that's the basic operation of how do you create a channel. So let's go back to the slides. Okay, can you see the slides now? Please confirm. Yes, okay, good. So this is the whole thing, the operation, and then how do you trigger. You can read here when the VGS is more than VT. VT is the threshold voltage. When the VDS is small, so what's going to happen? Thickness of the inversion layer will be created, or this is the channel. Relative charge density accumulated, then you're going to form a channel under the oxide. So just now we talk about NMOS, so N channel formation. So at the same time, you can also increase the VDS. So that means you're going to supply a VDS, a voltage across drain to source. So it will cause potential drop, cross oxide, and blah blah blah. So this is actually what's contributing to the formation of regions on the IV curve of the MOSFET. You boleh tengok the presentation one punya content untuk tengok what's going to happen at the different voltages and stuff. So this is actually ID VDS curve. So ID ni I drain current, and this one is the drain source voltage you apply across drain source to be able to generate a family of curve of MOSFET, right? So in this case it's an NMOS, so NMOS, N channel, macam kita draw on the whiteboard just now. So when you apply different levels of VG on the gate, so bila you apply different levels of VG on the gate, so we're going to end up with a family of curves. So the higher the VG, the higher that the curve is, right? So this is the saturation region. We're going to see later on saturation region. Ni kat sini, the first one is called ohmic region. Dia baru nak naik ya. This is saturation because it's plateau already, right? Ini sama. So but this one is for depletion mode because the channel is already there. So the TC is the thickness of your channel thickness, or inversion layer thickness if you like. So and this is the voltage requirement. You will see different voltage requirement. For example, if you compare right, kalau kita compare N-type enhancement and depletion, you can see here if you go to higher VG, higher than VT, you're gonna go up. So your curves are going to be higher than the previous one. Depletion mode, because the channel is already there, you need to understand how the transistor is turned on and off before you can understand this curve. Ni VT, this is the relationship, it's slightly different. So VGS is 0 is here, so VGS is less than 0, negative voltage. So this is where the VG gets positive. Okay, so negative VGS will induce a space charge region under the oxide, reducing channel thickness. This one is for depletion, for depletion. So negative VGS is required to induce SCR under the oxide, reducing thickness of the N channel region. So that means the moment you apply negative VG, you will reduce the channel thickness. So the reduced channel thickness will reduce the channel conductance. So channel thickness is proportional to channel conductance or the flow of current, right? So kalau you ada thicker channel, then conductance increases and drain current increases as well. On the other hand, if your channel thickness is reduced, your channel conductance reduces and your drain current reduces as well. So this is what we call modulating the channel, so controlling the channel. So modulate to is actually control. Modulate is equal to control. You can actually modulate the channel thickness by controlling the VG, either it's positive or negative depending on enhancement or depletion. Okay, so one basic requirement for this device is that the channel thickness must be less than the maximum induced space charge region. must be less than the maximum induced space charge region in order to be able to turn the device off. If your channel thickness is not less than the maximum induced space charge, you will not be able to turn off the device. It will just be on all the time. Okay, so it's a matter of identifying our channel thickness versus the space charge, maximum induced space charge region, and this can be done by calculation. So this is the summary of IV curve, ID-VDS curve for all types of the MOSFETs, right? All type of MOSFET, P-type enhancement depletion, N-type enhancement and depletion as well. So nanti you go through tengok dia punya ni the operation. Let me go through a little bit on the MOSFET. Now it's what, 9:40 plus. Okay, MOSFET, CMOS. CMOS is also called complementary metal oxide semiconductor. Selalunya kita tengok dekat the basic that we learn is called MOSFET. But when we talk about manufacturing or semiconductor fabrication like Silterra, Infineon and others, it's not called MOSFET, it's called CMOS. Kenapa kita panggil dia CMOS? Sebab dalam CMOS circuit tu dia ada combination of PMOS and NMOS. Zaman back then, in the 60s, in the 70s, memang orang fabricate PMOS separately or NMOS separately as a discrete device. Discrete device means satu je. Sekarang ni kita combine, in fact, multi-billions of transistors combination, and it makes a CMOS. So when we talk about CMOS, so it's actually a combination of PMOS and NMOS pair. So maksudnya dalam circuit yang sama, we have PMOS, NMOS, side by side in certain configurations. So that makes them complementary metal oxide semiconductor field effect transistor. It's actually MOSFET but in combination version, right? So the CMOS is used in integrated circuit chips like what we saw last time in Silterra, microprocessors, microcontrollers, memory chip, logic circuit, and other stuff. And CMOS is also being used in analog circuits such as CMOS sensors. Macam ni image ni, this is actually image sensor based on CMOS. Image sensor, CMOS base. So RF CMOS, highly integrated transceivers, many types of communication. It can be used in many other devices. These are only some of the examples. Right, if you look at the history, so MOSFET was first invented by these two scientists, Atala. This guy is an Egyptian guy. Egyptian. Atala is an Egyptian. Dewan is Teka. Dewan ni dari mana? What do you think? So you just tengok movie kan? Dewan sounds like what? From where? Teka. Sebelum kita habis kelas. Dawan can't. I don't know how to spell. I don't know how to. Yeah, exactly. Dawan is Korean. Okay, Korean. I don't know how to pronounce that, but it's Dawan. So it was invented. The MOSFET was invented back then, 59, in Bell Labs in the US, right? So originally, two types of MOSFET fabrication processes. So we have originally two types of transistors fabrication process for MOSFET, which are based on NMOS and PMOS. And at that time, back then, it was with 20 micron gate length. Gate length ni, before I finish, do you know what is gate length? Pernah dengar tak gate length? Can you see the whiteboard now? All right, good. So gate length, what is gate length? Before we stop, let me draw to you the gate length. Oxide gate. So when we talk about gate length, it's actually the width of this. gate length. So it's called gate length, right? Gate length or gate width. So we're gonna see tomorrow. This is also called technology node. Dalam MOSFET kita panggil dia gate length or gate width. But then when we go into wafer fab like Silterra, Infineon, MIMOS, Fuji Electric, and whatnot, it's also called technology node. It's actually the determinant factor of your transistor performance. If you want to pack more transistors into a silicon wafer, you have to make them smaller in size. So that means kalau you nak lagi powerful transistor, you kena push for lower gate length. Okay, you have to push for lower gate length. So back then in the 1960s, fabrication was done on 20 micron and 10 micron gate length. So that means the gate width that I draw just now was to 20 micron and 10 micron back then, right? So now the best one that we have in the world is around 5 nano. So just imagine what happens across the 60 years since 1960 to now 2020. So it has evolved. It has gone down from 20 micron to only about 5 nanometer gate length. Okay, so yep, and that's going to improve your transistor performance tremendously. Right, so I think I'm just gonna stop here for today. I'm gonna continue for the rest of the CMOS tomorrow, and I'm gonna give to you your presentation 1 assignment this week as well for the next 2 weeks. And before I finish, so we're gonna have your test 2 next week. Okay, test 2 next week. I'm gonna give to you your test 2 question on Wednesday next week. Nanti saya akan bagi further details. Konsepnya macam just like your test 1, it's an open book exploration kind of test. You're gonna be given long time as well, just like your test 1, and yeah, the rest is similar to test 1's concept. Okay, so anything on MOSFET today before I finish? Understood so far? Can you guys follow? Okay, so far so good. So please go to your friend's presentation on MOSFET to understand further on the creation of channel, step by step, ID, VDS curve. I'm not going to go in details because I've seen amazing videos on the MOSFET operation already, so you can just go there and try to understand from there. Okay, so we're going to continue with CMOS tomorrow, and we're going to finish with CMOS, and I'm going to do a review class, I think maybe this week or next week, and then I'm going to give you your time to finish off presentation 2, and we're going to have your test 2 next week, and then we're going to be done with our course very soon. Okay, alright, tak ada soalan all good. Right then, kalau tak ada soalan, then I'll see you again tomorrow inshallah. So bye bye, assalamualaikum, and stay safe.